Hey everyone, welcome to the start of a new series. Here we are covering all of the new content in year 10, and this is for the topics of measurement and geometry. Now, as I've mentioned at the start of previous series, these topic series that we've done, I'm only looking in this series at the new things that come up from the year 10 content. So this video assumes that you know a lot of these previous concepts, how to calculate areas and volumes and all these other things for a bunch of different shapes we've done already. Now, we are only looking at the new things. So in this video, we are looking at finding the surface area of a cone. Now, before we even get to this, I just want to do a quick little recap of something we talked about in a previous series, and this is how we can describe areas of sectors and areas of arcs. So, just a bit of a recap here because this idea is quite important. So what I've done here is I've cut out a sector out of this big circle, whose angle, I should say, is 250 degrees out of the entire whole circle. So if we were to find the area of this sector, typically we'd go, okay, well, we take the fraction of the whole circle, what this angle is, as a fraction of the whole angle that makes up a circle, which is 360 degrees. And what we'd do there is we'd multiply that by the area of the circle. Now, when we look at arcs here, just a reminder, the arc is just a portion of the outside of the circle. It doesn't make up the whole circumference, but it makes up a portion of it. And we said in a previous video that the way we find the area, not area of the arc, the length of the arc, because an area talks about space, a length is just the border here. The way we described the length of arcs is it was our fraction of 360 degrees. So 250 out of 360 degrees, and we multiplied that by the circumference. Now, that is the main background information I want to give you guys, because I want to jump straight into this idea of finding the surface area of a cone. So considering this here, and please be mindful of these examples we've just done, please make sure you're up to scratch with that, because that idea is going to be very important in the coming up with the formula for this particular surface area of a cone. So all cones, or at least the standard cones we're going to interact with in this video, we are looking at here regular cones. So it's a regular cone. Now, if we wanted to describe this shape, we would see that it has a circle on the bottom, as wonky as this looks. This is a nice, perfect circle down the bottom. Let's actually redraw that. Make it a bit nicer. There we go. We have a circle on the bottom, and it's going to have some radius r. And the way cones are constructed, right from the middle of this radius, there stretches up a perpendicular height, which we call h here. And you may notice that we have a perpendicular height both going from the bottom of the base, the middle of the base circle here, going to the top of the cone. And we also have another type of height here associated. Now this thing we're going to call L, and what this is, our L, is just our slant height. We're just using a different letter to distinguish this from perpendicular height like we've done before. So this is the height of the slanted bit of the cone. Think of like an ice cream cone. There's that slanty bit that goes all the way up to the tip at the top. So With this in mind, we want to break this up, as we did with all other surface area questions, into a net. And a cone is a little bit tricky because it's not immediately obvious that we can just point it out and count the surfaces like we would a prism, for example. But surface areas we defined before as the area of all the surfaces. So we just want to figure out what our surfaces are. So we have one down the bottom here. This is our circle down the bottom. So my surfaces I have here is my circle with radius r. And I'm going to draw you the net of the next bit, and we're going to just briefly talk about why that is the case. So I also have something looking like this. This is our curvy bit around the side. So these are our surfaces. Okay, now what's important to note is you guys can do this with a couple of sheets of paper if you'd like. You can cut out a small circle and cut out a slightly bigger circle and make some kind of cut going from the middle out to the ends. So what you're going to get is, instead of getting a full circle, you're going to get this shape here, which is going to be a sector. So this whole thing here is going to be a sector as opposed to a circle. So we're having a fraction of a circle, kind of like this idea up the top. Our sectors are fractions of an entire circle. Now, let's consider how these two shapes make an actual cone. So we're going to have this base circle down the bottom, and when we, for example, cut out this shape here, you guys can do this at home, and try folding it so that this little pointy bit here connects to this bit here. Fold it in and you will see this middle part pointing out. That becomes our pointy bit right at the top of our cone. So when we construct cones, well, we have our base circle, and then we're going to fold our sector here so that this line overlaps with this line perfectly. And what we're going to do once we have that, we are just going to match it and place it on top of our circle. Hopefully you can see that from this diagram. Now, we want to consider something, right? We want to say, well, this bit here, that's the radius of our sector here that we use to make the cone bendy bit. But what part of the diagram does this correspond to? Because once we fold it together, that makes the bit connecting the bottom, so somewhere like here, all the way up to the point at the top. So that particular bit there is going to be our slant height. So both of these radii are going to be the same as the slant height. If you want a bit of visualization on this, have a go at actually cutting these two bits, maybe draw it, cut it up, and see how it folds in. But you will notice that the radius of our sector in our construction of the cone becomes the slant height of our regular cone. Okay, now let's consider another thing in how this gets constructed. Because our thing, once we fold my arc here, so let's actually label that too. When we fold the arc, or when we fold these two bits together on our sector, the arc length has to fit perfectly onto the circular base, right? So what that's essentially saying is that our arc length, in order to make this a proper cone, our arc length has to equal the circular base. So it sits on really nicely, as we see here. So my arc length, let's actually do it down here. My arc length has to be the same as the circumference of my circle in order for this to be a cone. So I'm going to write here my arc length should equal the circumference of my small circle, which in this case is going to be 2 pi r. Now, let's not spoil the ending here. As right now, I'm just trying to give you a feel for how we can actually make these shapes. Why this formula isn't just an arbitrary thing that we've just come up with, but the reasoning for why something like this works. Okay, so now that we have our two shapes and bits that make up our regular cone, we need to have a think about how we can even make a formula here. I already know what part of my surface is going to be. I just need the surface area of my base. So that's pretty easy. The surface area of my base is pi r squared. But I need to find the area of my sector, which I don't know yet. So I'm going to consider something about how this sector relates to my entire circle here. And we're going to do a little bit of mathematical manipulation in order to be able to come up with an expression for my sector, because as it currently stands, I don't know my angle value, so I can't calculate my sector as I normally would. All I have is a radius of length L, this length up here. So I'm going to consider something. I want to consider how my sector relates to my whole circle, how its area relates to the whole area, as well as how its arc length relates to the entire circumference of the circle. Because a sector is just a part, a fraction of a circle. So we're going to say down here, and I'll explain this in a minute, but there is a relationship between the area of the sector and the area of the entire circle. Like I said before, in the same way there's a relationship between the arc and the relationship with the whole circumference. And that is this thing up here from what we looked at the start of the lesson. Notice that the sector, the area of the sector, 250 over 360, is the same as the proportion. It's proportional to the fraction of the circumference. So I can say, if I were to look at these as ratios, bringing some other knowledge from what we've looked at before, I can say that the area of my sector and how it corresponds to the area of the circle, so if I divided one by the other, it would give me the same thing as if I had the length of my arc and divided it by the big circumference, the arc over the big circumference. So now we have something to play around with, because based on what we know about sectors and areas of sectors and arc lengths, these are the same fraction of the whole. So we can set up this little equation down here. And now we want to plug in some values, because the thing we're trying to get to in the end is going to be this thing, right? So we have the area of my sector, And we want to now fill in these other three values. So this one here, this one here, this one here. And we want to plug all of those in order to find an expression for the area of my sector. Okay, so the area of my circle, or the area of my big circle here, is going to be pi times the radius squared. But what is the radius in this case? The radius is L, the length L. So I have the area of my sector over pi times the radius all squared. And that equals to the length of my arc. So remember here, my arc has to fit perfectly on my small circle. So the length of my arc is the same as the circumference of this smaller base circle, which is 2 pi r. Now, the length of my arc, therefore, is going to be 2 pi r. And my big circumference, that's going to be my entire thing here. So 2 pi times the radius of this bigger circle. Now this radius is actually L here. So the radius, the big circumference, the circumference of my bigger circle is going to be 2 pi L. And now I want to solve this equation here. I want to get the area of the sector, my expression for this, on its own. So to solve this equation, I'm going to times both sides by pi L squared. I want to undo the dividing with this denominator here to give me the area of my sector on its own. So I'm going to times both sides by pi L squared, which gives me the area of my sector being 2 pi r over 2 pi L multiplied by pi L squared. Okay, now we can make some simplifications to this. We have a 2 pi on the top and a 2 pi on the bottom. Both of these will cancel out. And I also have an L on the denominator here, but when we multiply by an L squared, which is going to give us something on the numerator, then one of those L's is going to cancel with one of these L's. So the area of my sector becomes, what do I have left? An R, a pi, and an L, all multiplying by each other. So that gives me pi times R, the radius of my base down here, just to clarify, and L, which is my slant height. So that's how I can find the area of the sector. I want to multiply all of these together. So putting this together, we have two different areas that make up the surface area. The circle here and the sector on the right hand side. So I need to add those two to get my total surface area. So I can say, therefore, the area, or the surface area of the cone, equals pi r squared, my smaller circle, plus pi r L. So that is how I can find the surface area of any regular cone. Now, first half of this video was just explaining how we come up with this formula in the first place. If that's useful to you, that's fantastic, but I'm sure some of you just want to get straight into working through some questions. So if you've made it this far, thank you, but we will now get to some actual questions here and look at how to apply this formula here. Okay, so we have a cone with a radius of 2 meters and a slant height of 4.5 meters. And we established before we have our surface area formula. So that surface area is going to be pi r squared plus pi r L. And now I just want to substitute my values in. I have a radius down here, which is going to go here and here. And I have a slant height here, which is 4.5 meters, which is going to go into here. So I'm going to get pi times 2 squared plus pi times 2 times 4.5. And we're going to find this to 2 decimal places. So when I substitute this all in and put it into my calculator, I'm going to get 40.84 meters squared. Okay, let's try one more question to wrap this up. I have another cone, and this time I have my radius, and let's make that 5 centimeters. And this time I have a perpendicular height of, let's go 7 centimeters. Okay, now because this is a perpendicular height, I'm going to draw in a little right angle here. Now, we encounter a problem when trying to do something like this, because I have an area of pi r squared plus pi r l. These are my particular values or bits from my formula that I need. So I need to identify these on my shape. Now I have a radius, which I can substitute, but I don't have a slant height yet. So I need to find that. I have an L here, but it's unknown at the moment. But if we notice, there is a right angle triangle that is embedded within my cone. So that means that we can do something we've learnt with triangles, right angle triangles, in order to find the L. Because this L here is the hypotenuse of my right angle triangle. And I can use Pythagoras' theorem, we're bringing this back once again, in order to find this length here. So first I want to find my slant height, L. And to do that, I know that my hypotenuse squared, or my c squared here, is going to be the addition of my 7 squared and 5 squared. So that means my length, I can express that by solving this equation. So if L squared equals 7 squared plus 5 squared, I can find L by taking the square root of both sides. And that is going to give me the square root of 7 squared plus 5 squared. And I'm just going to leave this as a surd, as just a number under the square root, because just for accuracy purposes, when I substitute in later. So I'm going to leave this as a square root of 74, which is 7 squared and 5 squared added together. Okay, now that I have this L, I can substitute it back in. I can now, using this relationship of a right angle triangle to find my unknown slant height of L, I can now find the surface area of my cone. So now it's time to substitute everything in. So my area is going to be pi times my radius of 5 squared, and that's going to get added to pi times 5 times the square root of 74 here. And let's just do this to 1 decimal place. So when I plug this into my calculator, I will get 216.7, 213.7 centimeters squared. So this is a two-part video. Hopefully the second half has given you an idea of how to actually use the formula. And the first half, if it's relevant to you, if you were just curious, we looked at a way to actually break down our cone into its parts and come up with an expression for the entire surface area. The area we get when we add the circular base with the sector which makes up the slanty bit up here. But that brings us to the end of the video today. Thank you so much for watching, and I will see you in the next one.